Hello and welcome to our presentation about context-aware robot control using gesture episodes. This is a joint work with K.Stepanova and K.Stepanova. Here you can see the overview of the proposed system. The goal is to be able to communicate with the robot using intuitive hand gestures. The robot should estimate the mapping between the gestures and the desired action, taking into account the context of the situation, such as manipulated objects, operating user, or position of the objects. Related work is focused on development of wearable gesture recognition sensors and on human-robot interaction systems featuring gesture detection. However, these works often lack context awareness and have low gesture expressiveness. The main contribution of our work is a flexible gesture recognition framework that is context-aware and supports combination of different gesture types. Now we will describe the individual components of the proposed system. The input to our system are features extracted from the hand movement by leap motion sensor. On these data we run two gesture detectors, one for static gestures and the other for the dynamic gestures. Afterwards, the probabilities of different gestures are merged with the context data such as scene, user, or probable target objects. We use probabilistic neural network to map these observations to user intent. When the user intent is detected, the corresponding robotic actions are generated. For our setup, we use Frank Panda and Copilot Simulator. Let's see how the gesture classification is done. We run two gesture detectors, the static and the dynamic one. The static one, shown on the left, uses probabilistic neural networks. It takes as input all 57 hand features of a given time frame and outputs categorical distributions over gestures. The dynamic gesture detections shown on the right uses a probabilistic motion primitives based on gesture representation for the palm position and rotation over time. Dynamic time warping is used to measure similarity between the observed trajectory within a sliding time window and the learned probabilistic motion primitive. For the gesture detection, we use our gesture toolbox. It performs online gesture detection for all defined gestures. In this work, we use a set of 8 static and 5 dynamic gestures. The set of gestures can be easily adjusted. Check out the code on GitHub. The sequence of gestures is naturally divided into episodes by hand visibility. We compress the gesture episode into a vector of maximum probabilities for each gesture, which is subsequently used as input for the classification. Let us explore the mapping of gestures and context to human intents. In the teleoperation case, the user wants the robot to execute certain actions that contribute to a long-term goal. Pouring, opening, closing drawers, and pick-up place are typical examples. We formalize a human intent as a triple of target action, target objects, and further auxiliary parameters. Consider, for example, pouring the content of the cup with a target angle of 40 degrees. For our experiments, we created a set of target actions, target objects, and parameter types. We pose the intent estimation task as a supervised learning problem, specifically a classification task. From the gesture recognition data G and the scene context C, we want to find the most likely human intent. Therefore, we generate a dataset of feasible intents in different simulated scenes. First, we create a random scene, then we select random target action and object, provided some common sense knowledge about the action in feasible combinations are avoided by the sampler. Lastly, a fitting gesture is sampled from an n-dimensional conditional rule table. Here you can see an example of an action execution for action put with target object drawer. As a result, the trained network can select suitable intents based on the scene. Here you can see the swipe down gesture with a focus on a cup is interpreted as pickup cup. In the same scene with the focus on the closed drawer, the swipe down gesture is resolved to the intent opening the drawer. Finally, conditioning on different user profiles is possible. Here, the robot decides to pick up the cube on the left because the training data is biased differently for each user profile. We created different datasets D1 to D4 with increasing complexity to test our approach. In the more complex scenes, we allow, for example, different actions for the same gesture when focused on different objects. As we saw before, swipe down can mean in different contexts open drawer or pick up cup. To cope with the increased complexity, we devise 5 neural networks models and 1 to M5 with increasing number of parameters. All models are able to learn the mapping in D1 with the given amount of training data, but the more complex models have high learning capacity to capture even the intricate dependencies of D4. Now let us see how the robot action is managed. In general, our system should only generate feasible actions. Nevertheless, we designed a behavior tree for the experiment domain encoding all the common sense knowledge about feasible actions. We write the identified intent to the behavior tree blackboard, and the behavior tree will then coordinate the robot's actions towards fulfilling the intent. If required, the robot would open the drawer before it puts object in it. So, the contributions and takeaways message are: we propose a system that infers the human intent from gestures and context of the scene. The robustness and usability are increased due to a higher level of robot autonomy. We evaluated the core system components with ablation studies and conducted tests with user-operating simulated robots, and since then also conducted experiments on the real Frankai Mecha Panda. Thank you for your attention. Feel free to check out open source code accompanying this paper and contact us if you have any questions. Thank you.